was called Mad, just restarting its skills. Okay. So, sign convention. We're getting into the good stuff. I dislike most country music, as we've established, but there's this song that is.
Established this? When did we establish
I don't remember if it was this class that we established it. But so I like old country music, some of it, not all of it, but the new stuff I really can't stand. But my wife does like listening to country music, so I have heard way too much of it. And so, like, you know that song, The Good Stuff?
Yeah.
That's going on in my head right now. And I dislike it.
Oh. It's not the good stuff.
This is not the good stuff. Okay, but we're getting to the point where we can draw linear graphs for different systems, and we're getting hopefully excited about that fact. Sign convention, though, is pretty key, so I want to talk about that today. We're only going to cover the first two types of sign, or of energy domains today. We'll cover rotational mechanical systems on Friday, but I thought that it would be good to at least start this today. So the sign, positive or negative, of a variable is used to represent an orientation of its physical quantity. For instance, negative 3 meters per second could mean 3 meters per second to the right or to the left, right? For instance. It could also be up or down, or like this way or that way. Yeah. But you guys are a little bit familiar with that already. No one can say which is better, left or right. Okay, right is better. Deciding how the physical quantity corresponds to the sign of the variable is called sign assignment. And yes, I want to do a pun with that, but I'm going to try to refrain. When we use a sign convention, we make the assignment in a conventional manner. For instance, the sign convention for normal stress is that compression is negative and tension is positive. Okay. So we could have gone with the other way, but the convention is to do normal stress, negative for compression, positive for tension. Why use a sign convention at all? If we follow a convention when constructing a problem, we can use the convention's interpretation of the result, which is convenient. For complicated systems, this helps us keep things straight. Furthermore, if someone else attempts to understand our work, it is much easier to simply say, using the standard sign convention, than explaining our own snowflake sign assignment. I wear this like snowflake badge as like a sign of honor. It's kind of fun. However, it is nonetheless true that we can assign signs arbitrarily. Arbitrary, vive la révolution. However, if a source is present, we must observe some caution. A source typically comes with its own convention, okay? So we need to be a little bit cautious. We can technically arbitrarily assign signs even to sources, but it's not a good idea. So, for instance, if we hook up a power supply to the circuit with the plus and minus leads a certain way, unless we want to get very confused, we should probably accommodate that sign, right? So if you're given a circuit that has like the plus and the minus leads connected from a source already, technically you can assign it whatever sign you want, but you're going to have to then come up with some confusing interpretations where positive voltage in is actually negative voltage in your circuit, which is just not not a very convenient way to go. So typically we accommodate the sign of the source. Whatever the source comes as, we accommodate that and integrate it into our circuit. A sign convention for each of the energy domains we've considered thus far follows. So the electronics one is actually very familiar to us because we already have looked at it before. We use the passive sign convention of electrical engineering defined below. So power flowing into a component is considered to be positive, and power flowing out of a component is considered to be negative. All right? Because power is the product of voltage and current, this implies the current and voltage signs are prescribed by the convention. For passive elements, the electrical potential must drop in the direction of positive current flow. This means the assumed direction of voltage drop across a passive element must be the same as that of the current flow. For active elements, the opposite's true. So active elements are our source elements. The voltage drop at current flow must be in opposite directions. So figure 4 or 2.4 illustrates this. So we're now using our nice, sexy linear graph branches instead of our electronic circuit diagrams, but not much has changed, right? For circuits, it's like kind of pretty much the same thing. So across some element, passive elements don't have the circle. Active elements or sources have the circle around them, right? So on the left we have two passive elements, and we're showing the two possible configurations. So maybe the voltage drop, assumed drop is from top to bottom, in which case the assumed current flow must be also in that direction. Well, maybe the assumed voltage drop we're going to take to be from bottom to top. That's fine, as long as we also make the current flow assumed in the same direction. And those are both in the same direction as, and we actually typically just denote this with the direction of the arrow. We don't draw the green arrows on here typically. We just use the arrow that's already on the branch. Okay? And on the right side, we see an active element, two active elements. So in this one, the assumed voltage drop is from top to bottom. And notice that the arrow we draw is in that direction of voltage drop. And that is what we'll use as our convention for drawing these source elements. Whenever we have a drop, we draw the arrow in that direction. And so the direction of current flow is opposite for a source element. So voltage drop one way, current flow the other way. The reason is that the product of the power, or the product of the voltage and current is power, right? So for active elements, they're providing power to the circuit. And when they provide power to the circuit, that's going to be a negative power, because we say that power going into an element is positive, so power leaving an element has to be negative. That's our convention. Could have gone the other way with it, but alas, we are stuck with this one. Well, I mean, you guys can do what you want. Just explain the convention you're using in any problem, or just use this one. I recommend using this one. Cool. So when drawing a linear graph of a circuit, for each passive element's branch, draw the arrow beside it pointing in the direction of assumed current flow and voltage drop. The purpose of a sign convention is to help us interpret the signs of our results. For instance, if at a given instant a capacitor has voltage of 3 volts and current negative 2 amps, we compute the power to be the product of those, right? So 3 times negative 2 is negative 6 watts. And we know 6 watts of power is flowing from the capacitor into the circuit because it's negative, so that means the power must be flowing out of the capacitor. Okay? For passive elements, there is no preferred direction of assumed voltage drop and current flow. If a voltage or current value discovered by performing a circuit analysis is positive, this means the assumed and actual directions are the same. For a negative value, the directions are opposite. Okay? So when you come up to a circuit element, just like we've always done, a passive circuit element, we just draw an arrow in any old direction, and that's the direction of assumed voltage drop and current flow. If the sign comes out negative, we know it's actually going the other way. So the interpretation is pretty easy. For active elements, choose a sign in accordance with the physical situation. Like we talked about, if a positive terminal of a battery is connected to a certain terminal in a circuit, it ill behooves one to simply say, but darling, I'm going to call that negative. It's positive whether you like it or not, Nancy. That was a joke I reused, but I liked it. Okay. I gotta have fun with making these notes. You can tell. I just like sitting there just like, hee 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 hee. That's what I do. I laugh like that. Okay. Any questions so far? The electronics one is pretty familiar to us. We already used it, so.
When you say that the current is flowing out of the capacitor, if you were to draw that like on a circuit diagram of a capacitor, for the sake of the sake, our directional arrow would be pointed along the circuit.
So
I'm kind of struggling to picture that in terms of a
yeah.
diagram.
So let's look at a capacitor. So let's say that we drew a linear graph element, a branch representing it, just like that. And say we were assuming the current was going to flow in this direction, so we're going to assume current flows in that direction on the element as well, or on the branch as well. So this is, so it's a typical situation. Now, if we were to compute the voltage and current across this capacitor to be, so in this example, I said 3 volts, and the current was negative 2 amps. That would mean that the voltage drop from this side here down to this side here is 3 volts. So this could be like 6 and this could be 3, or this could be 9 and this could be 6, as long as the drop across it is 3. And the fact that it's positive means that it is larger on this top side than it is on the bottom side, in the same direction that we assumed that the drop went. Now the current being negative 2 amps means that instead of the current flowing in this direction like we assumed it would, actually current's flowing in the other direction. So current's actually flowing this direction. And that's opposite the direction that we assumed it would flow, so it comes out negative. That negative sign comes. And if we compute the power, then we take the product of the two, right? We get negative 6, not amps, watts, right? So that is power. You could think of power leaving this capacitor is 6 watts. So maybe you've charged up the capacitor, and now you're discharging it into the circuit.
Okay.
Does that make sense?
That makes a little bit more sense.
Cool. When the capacitor is charging, power's going to be flowing into the capacitor. Cool. So let's talk translational mechanical systems. These kind of increase in difficulty, I would say, with the sign convention. Actually, the textbook pretty much just punts on this point. It almost does not talk about a sign convention for translational mechanical systems or rotational mechanical systems, but I think it's important. I mean, even though I know a professor, very good professor, who totally just punts on this too. Like, he just doesn't teach the sign convention for mechanical systems because he thinks that you could get really bogged down in it, spend a lot of time, and nobody actually learns. So I think it's worth slowing down and talking about, though. I mean, we might not get a full understanding, but we should at least have an idea of what the sign convention is. And I actually think it's not too bad. So what I do, instead of defining it in broad terms, I just give a procedure for constructing a system with a sign convention and interpreting that sign convention. So we'll see how this goes. So the following steps can be applied to any translational mechanical system. We introduce the convention with an inline example, which is going to be happening over here on the right. Consider the simple mechanical system here. So we have ourselves a fixed reference here. So this is sort of patchy looking, but it's ground. And this is a spring element and a mass element. And we have a force source that's applied to the mass element. Okay? So we're going to use the following procedure to construct the signs. So first, the coordinate arrow. Assign the sign by drawing a coordinate arrow as shown at right. So I just drew it to the right. Okay. The direction of the arrow is arbitrary. Could have drawn it to the left. I really couldn't have drawn it up because that wouldn't have been helpful for this problem. So in the direction of motion that we're considering. So direction is arbitrary. However, if possible, assign the positive direction to match the sources. If the problem allows, it is best practice to have all sources and the coordinate arrow in the same direction. Sometimes you have sources that are pointed in the opposite direction within the same problem, multiple sources. And you just can't do anything about it because you can't choose a coordinate arrow that's in the direction of all the sources because they're pointing in opposite directions. So but oftentimes we can assign what direction positive is for the sources, and especially in a mechanical system. In an electrical system, you're stuck with like the plus and minus terminals of the source. In a mechanical system, oftentimes a force source is there to represent like some input interaction with some environment, and we can often assign the sign of the source in any direction that we want. So when we do it, we should assign our sources all in the same direction as the coordinate arrow, if at all possible, because it makes the interpretation a lot easier. So that's just my recommendation. Okay. So I drew it in the direction of the coordinate arrow, or in the direction of the force source to the right. Okay. Now draw a linear graph without arrows. So there are two nodes with distinct velocities, ground and mass, as shown at right. So this represents, I drew it sort of So we usually will construct linear graphs with the ground on the bottom, or often we will. And then we'll have, nodes up here and what all is going on. So that is more common, the orientation, but sometimes it's actually convenient to draw it sort of sideways so that it corresponds more to the physical situation. So we have this problem that goes left to right, and it has this ground on the right. So we're going to draw our linear graph in that orientation. It'll just help us out. I think it's a little easier. So we draw with the ground on the right, and then we have two distinct velocities, I claim. One is the ground. So the ground is definitely, it's always a distinct velocity. So it's always a node in our graph. And then we have the mass, which also has a distinct velocity. The mass has a distinct velocity. The ground has a distinct velocity. There's no other one, really, because the spring connects in between those two. There's no other node that really makes sense here. If you're considering a spring as a lumped parameter element, a mass as a lumped parameter element. Those are the only two distinct nodes. So this represents the mass node, and this represents the ground, right? Now, the mass node is always drawn to ground. And that's because we need an inertial reference frame for the mass, right? So the mass is always drawn to ground. In fact, sometimes we draw it with a dashed line to say it's sort of like virtually connected to ground, because of course the mass isn't directly connected to the ground, right? But so sometimes we'll dash this line in the latter half of it just to show like, oh, it's virtually connected to ground. But you don't have to dash it. That's just like to remind ourselves that it's not a real connection. Okay, so we draw the mass from the mass node to ground. Then we connect, so the spring connects between the mass node and ground. It physically does, right? So the spring is in between the mass node and the ground node. It connects to both. So in the linear graph, we have to draw it between the mass node and the ground node. And then finally, the force source connects to the mass where it is applied. So it always connects to the element that it's applied at. So it's applied to the mass node. And we usually take ground to be the other side of a force source, because you can think of the force as originating at some fixed point or some inertial point and being applied. But the ground is impervious to this force that is being applied here. So it's not like we're connected to another node which can feel that force. The ground is impervious to the force. Okay? All right, so that's our linear graph. And it's actually, until we get more comfortable with the sign convention, I actually recommend that we do this first. We draw the graph with no arrows. Eventually we'll get comfortable enough that we'll be able to assign the arrows as we draw them, the elements. But for now, I think it's best to just draw the whole graph and then assign the arrow directions. Okay. Any questions on the graph?
When this system, would it only be used for like a simple, or not necessarily simple, but only a one force system? Is it only going from state 1 to state 2, for example? I was thinking we had to do physics problems where you have like two masses connected by springs to, in this case, ground or a wall.
Mm-hmm.
Would then you have to draw like multiple lines to go there? I'm just
Yeah.
This is more
So
about
actually, we're going to do an example right here. That's going to be two masses connected. Yeah. Yeah. But it's, I mean, there are the methods that we're developing are going to allow us to do any number of elements. And actually, I think that where this method really shines is when you get to those higher order systems, because they're not really any harder than the lower order ones.
Just more.
You have to just write more elemental equations, etc. But there's really just it's the same process. You don't have to like sort of feel your way through the problem. It's just a systematic algorithm you can go through. Yeah. So, all right. Assign spring and damper directions is the next step. So on each spring and damper element, define the positive velocity drop to be in the direction of the coordinate arrow. So we go back here and we say, well, the mass element goes, we say it actually, we're going to only deal with the springs and dampers first. So the springs and dampers, there's only a spring, right? There's no damper in this problem. So with the spring, we have to assign it in the velocity drop in the direction of the coordinate arrow. What that means is that it goes from the mass node to ground. If our coordinate arrow was drawn on the other way, it would go from ground to the mass node, right? So we assume the drop to be in the direction of the coordinate arrow, which is, if you follow that arrow from left to right, because that's the direction it's going, left to right, you encounter the mass first, and then you encounter the ground. So from mass to ground, so your direction is going to be towards the ground. And we drew it sideways, so that allowed us to draw it really in the same physical direction towards the right. But if we had drawn our linear graph oriented vertically, then it would have, this arrow would be pointing down, right? But really the big takeaway is it goes from the mass node to ground. That's the key. Left or right just depends on the way that we orient the graph. All right, so that's the spring and damper one. And then we assign mass directions. So on each mass element, so masses are easy, define the positive velocity drop to be toward ground. Masses always connect to ground. So just always draw the arrow towards ground. Assign, so each of the elements this way. So we already had, oops, I drew that arrow up on that one. I wanted to draw it there. Now we're building it, so it's still, spring is that way. And now we said the mass is also towards ground. I said sometimes we dash this mass element here on the latter half to let it be shown that this isn't a real connection to ground, it's a virtual connection to the reference for the mass. All right. Then assign force source directions. So on each force source element, define the positive direction as follows. The ideal case, so if you can construct things to work out in this ideal way, it's best, but it doesn't have to work out this way. If the force source has the same definition of positive as your coordinate arrows, draw it toward the node of application. Okay? So we still have our spring and we still have our mass this way. Now, our force source, we want to draw it, so if the force is in the same direction as the positive coordinate arrow, draw it toward the node of application. In our case, that is the situation, right? Our force source definition of positives to the right. Our coordinate arrow is to the right. It's the same, right and right are the same. So that means that we draw our force source direction arrow towards the element of, or towards the node of application, which is the mass node, right? So if we come here, it's going to go towards the mass node. If needed, we will have this other situation, which is the source having the opposite definition of positive as the coordinate arrow, which is not our situation in this case, but if that was the case, we would draw it away from the node of application. Okay, so if, for instance, our force source positive was to the left, then it would be opposite our coordinate arrow. We would have to draw the force source arrow this way, down towards ground, away from the node of application. But that's not what we have. All right. So, finally, assign velocity source directions. On each velocity source element, define the positive direction as follows. Ideal case is if the velocity source has the same definition of positive as your coordinate arrows, draw it away from the node of application, so it's the opposite. And we don't have a velocity source in this problem. This is a force source. However, and that's why I made it a cloud here, because this is like, imagine if, right? Imagine if it was a velocity source. And so these are unchanged. If it was a velocity source instead of a force source, then, and it was pointed in that same direction as the force source is pointed, so that's just like pretending like, this is our cloud here, pretending like this is a velocity source, Vs, that's being applied. It's in the same direction. Then instead of drawing it in the direction or towards the node of application, we actually draw it away from the node of application. So it's the opposite of the force source. And then if needed, if the velocity source has the opposite definition of positive, then draw it toward the node of application. So if our velocity source was pointed to the left instead of to the right, then we would have the arrow here pointed left instead of right. Okay? All right. How do we feel about that? Let's do an example. Oh, but first let's talk about interpretation before we do an example. So, it's all great, right? Like you assign the arrows in this way, fine. But the real power of a convention is typically in the interpretation. So, convention yields the interpretation of table 2.1. Sexy table 2.1, I should have said. So, interpretation of translational mechanical system sign convention. On the left side of the table, we have force interpretations. On the right side, we have velocity interpretations. The rows correspond to mass, damper, spring. Okay? And if we have a positive value of force or a negative value of force, that's these sub-columns here. Positive value of velocity, negative value of velocity. So this is the interpretation that we can take. So say like you ended up with a mass force, so the force on the mass, Fm, came out to be equal to plus 3 newtons. That would put us in, so we're talking about a mass, we're talking about positive, because plus, and it's a force, so that puts us right here in this first cell, which is, the interpretation is, force is in the direction of the coordinate arrow. Sweet. That's nice. All right. So now for the negative, if a negative sign came out for that same force, so say instead of having a positive 3 newtons. We had negative 3 newtons. That would mean we're over here, right? We're not in this one anymore. And the force is opposite the direction of the coordinate arrow. That's the interpretation. Okay? Say we had a force on being transmitted through a damper, and it came out to be positive, okay? Then damper force positive is a compressive force on the damper. If it comes out negative, it's a tensile force on the damper. Similarly with the spring, and it's the same as the damper as far as force goes. Okay, velocity. If it comes out positive, then velocity is, for a mass, if it's a positive velocity, the velocity is in the coordinate arrow direction. If it comes out negative, the velocity is opposite the coordinate arrow direction. For a damper, we mean that the velocity drops in the coordinate arrow direction, and if it comes out negative, we know that it drops opposite the coordinate arrow direction, and similarly with a spring. So, yeah, that's our interpretation. So let's do one. Should we do one? I feel like we need to. All right. This is, what order do you guys think the system is? Just like second. The two masses made us think second, right? Actually, this is going to be third order.
Is it because of the dampers?
It's because of the spring. It's because we've got a, if you just have a mass and a spring connected to ground, for instance, that's actually a second order system.
Oh shoot.
If you have two
I missed
masses connected by a flexible element, you're going to have a third order system. So yeah, so this is going to be a third order system. We're not going to do the analysis all the way through. All we're going to do is construct a linear graph and assign sign convention, or assign signs according to the sign convention. So that's what we'll do here. So we've got, we have another left to right sort of problem. So let's draw the linear graph in the same sort of sideways configuration. So we'll draw ground there. What other nodes do we have? We always have the ground node. What other nodes do we have? Mass 1 and mass 2. Yeah, those are our other two distinct velocities, right? Mass 1 and mass 2. Now, there are different ways you can go with this graph. I mean, so I think we'll just stick with a nice, like, we'll put the mass 1 node here and the mass 2 node here. And maybe I'll move this over so that it's like actually in line with the ground. So we can draw them like that. Now, in a lot of cases, we would actually, because we know we're going to have to connect this mass 1 over here to ground, it's kind of awkward to draw these long arrows, so often we wouldn't orient it exactly this way. But when we're first starting, it's kind of nice to orient them in the same way, right? We get away from that once we get more comfortable with these graphs, but for now, we're still a little uncomfortable. So the first thing that I like to do when I look at these is I like to put in the sources first, because that's always a nice way to start. So we have a force source coming in here, and it is going to usually be connected between ground. If it's an external force, we connect it to ground and then to the node that it is applied to, right? So this one's applied from ground. So we can label it Fs. We haven't decided the direction that it's going to go yet. We're going to leave that till the end. We'll just construct the graph first, and then we'll draw the arrows. Okay. And then we've got ourselves, so the mass 1 and the mass 2, they have to both connect to ground, right? Masses always connect to ground. So let's go ahead and connect them to ground. And what the hell? Let's do the dashing thing because it's kind of nice to say. They're virtually connected to ground. So M2, and then we've got our oh, I didn't do the dashing on that. I'll do it.
So what's going on?
This is our mass 1 element. So what we're saying is mass 1, this node associated with mass 1, we draw the element for mass 1 from the node associated with it to ground, always, because a mass always has to have a reference to ground. And we do the dashing just to remind ourselves that, I mean, the mass isn't actually like bolted to ground, right? Like it's not, there's no like actual physical connection to ground, but we always reference it to ground. So we do this dash just to remind ourselves of that. We could just as easily, and I don't care if you guys decide to draw the dash or not, you could just do away with the dash and just draw it to ground. That's fine. Either one's fine. So we got our masses that go to ground. And then we've got our sort of physical connections, right? So between mass 1 and mass 2, we have a spring and a damper, right? So between which nodes should I draw the spring and the damper?
1 and 2.
Yeah, between mass 1 and mass 2. So we've got B1, and we've got, oh, I drew the arrow. Shouldn't have. And then we've got K. I also drew the arrow on the masses, but we'll deal with that. And then we've also got one more element. And where's that final element? B2. And where does it connect? To ground. Yeah, good. So that is B2. Okay. Good. So now we just need to assign our arrow directions. And arrows are, our first one was to do the source, or no, first one was to do the spring and dampers, right? So the spring and dampers, it doesn't really matter the order you do them, actually. Spring and dampers, we draw them, first, before we do anything with the sign convention, what do we need to do? Or the sign assignment, what do we need to do? Yeah, draw the coordinate arrow. So let's draw our coordinate arrow to the right. Why did we choose to the right? Because right's always right. No, because it's the direction of the force source that's drawn, and we like to keep them in the same direction if possible. So that's the direction I drew the force arrow. So let's draw the coordinate arrow in that direction. That means that our K and B1 are going to have direction what? So remember, it's in the direction of the coordinate arrow. So from mass 1 to mass 2, because if you go left to right, you encounter mass 1 before you encounter mass 2, right? So it's going to be from the mass 1 node to the mass 2 node. And then it's the same with B2, right? It goes from the mass 2 node to ground. So B2 is also going to go that direction. Masses, I drew the arrow of the masses when I drew the mass elements because they always go to ground. So it's really easy to do that one. The mass references always go to ground. And then finally, we have our source. So our force source, we have to decide if it's going to be it's going to be in the direction towards the node where it's applied or away from it. In this case, we have a force source in the direction of the coordinate arrow. Okay? So that tells us that it's toward the node where it's applied. So the force source is that direction. All right, any questions about that? So I'm going to tell you guys something that is kind of maybe shocking to you at this point. But you can automate the rest of this. So you come up with a linear graph. We could write a computer program that could take this linear graph and give us the equations and solve them. Which is pretty sweet, right? So we're going to learn that algorithm, and it's important to learn that algorithm. But realize that being able to construct this is the part where the engineer is still going to have economic value for some time. The rest of it can be automated. This first part is actually something that there's some interpretation in how you assign things and what's connected to what. But once you connect it up, the rest of it can be automated. Okay? I mean, I don't want to like be defeatist, but I'm trying to convey is that constructing this, don't feel like, oh, this is the trivial part, and then we're going to get to like the important stuff. Like constructing this graph is actually the important part. Okay? All right, that's all we've got for today. Yeah.
I want to know how